I welcome all the participants for this third day ATAL FDP program, which tells about your different type of materials. And the title itself, we coined that as TEAM, that is theoretical and experimental approaches of material, because materials rule the world for a long time. This from Ice Age, Stone Age, and etc. So last 2 days we have discussed with some materials, space materials. Yesterday we have discussed about space material, optoelectronic materials, then magnetic material. Then the first session is about the crystalline materials. And today we have a very special speaker with a very strong background in chemistry. And I'm very happy that he was my colleague and friend during my PhD period. It was very nice. Always the studying period is a happy period for all of us. And especially in college, we spent a very good time in Madurai Kamaraj University as PhD student of SOP, that is School of Physics at Madurai Kamaraj University, myself, and my friend and professor R. Suresh Kumar as scholar at School of Chemistry, because the School of Chemistry is much bigger than us, and they have very good facilities. And we enjoyed a lot, and we discussed a lot. And it's very immense pleasure to invite my best friend and my colleague, Professor Suresh Kumar sir, for this event. And he completed PhD Madurai Kamaraj University during the year of 2008, I think so. And
Yeah.
yeah, then he served different places as a postdoctoral fellow at Malaysia Science University. Then he started his career at Assistant Professor in South University, Saudi Arabia. Then associate professor at the same institute. Now it's very happy that he's serving as a professor at King Saud University, Saudi Arabia. It was a very long journey at Saudi Arabia with Suresh Kumar sir, and he did lot of works, especially the researches he carried out. Always that is shown in for everyone. It is shown in their H index values, and the H index of Suresh Kumar is almost is going to reach 10,000, 9,408 in Google page, and 44 is H index, and sorry, 9408 is citation, and he did lot of reviews on journals, and he got many awards, and also he done good number of projects and guiding the students and etc. It was very immense pleasure to you, Suresh Kumar sir, and we decided to have many people to be address many materials. So the your team 20 or this FTP will be look like a spectrum which involve all kind of colors and all kind of materials in such a way that you are going to present a very good thing, because as a chemistry person you can present very good things with us, and with this, and also you are the first person to from chemistry background, and for the last 2 days we had from physics and engineering backgrounds, and today we are having you, sir. And with these words from you, the session is handed over to you, sir.
Thank you. Thank you very much, Dr. Radhi, for your nice words.
Thanks.
So as you said, I think we had very good time at Madurai Kamaraj University during our PhD days. So I'm very happy when I'm thinking those days, it's unforgettable days.
Yeah.
So it's very happy to remember those days. So good evening to everyone. So today we are going to deal with the synthesis and applications of advanced materials. So advanced materials means advanced polymeric materials. So they are also called as smart materials. So in general, human life mainly depends on living and non-living things. So during the Stone Ages, so humans used stones as materials. So to lead a good and comfortable life. So after that, later during the Bronze and Iron Ages, so when bronze and iron materials are discovered, so they have a betterment of life. So the life of human being, people, so to some extent, I think they had a better life. And also when during the rubber and steel ages, and also in polymer ages, when ceramics, rubber, and polymers are discovered, so that a much better life when compared to the previous years. So recently, not recently, it's actually 1 or 2 days ago, when nanoparticles are synthesized, and so their applications has been widespread. So now the future of today is it's advanced materials, advanced polymeric materials. So here I think we will discuss about the advanced material. So this shows the comparison of lifetime of materials with and without incorporating self-healing properties. Smart materials are self-organized materials, so stimulating itself based on their environment. For example, when a material is repaired or get fractured, so the properties itself, I think it will self-heal the material and it will regain its initial properties. And it will become like an original material. So this is the property of self-healing materials. When you see the original material, so every material has a lifetime. So here, this is the point when it gets fractured. So after that, the mechanical stability of this material will decrease, and the property of the materials will also get degraded. And also, when a mechanically reinforced material, some support has been incorporated, so even this material has some lifetime, so that is little better than the original material. And even here also, the material will degrade as the time passes on. There are some available materials, self-healing materials. So here with some labile bonds and these materials. Here also, after the initial fracture, so when the material degrades, and this point when it reaches here, so it will regain its properties, and it will act as the original material. Even in these two cases also, even though the property of these materials are regained, so their stability is less as the time passes on. So now the future of our research is smart materials. For smart materials, so for example, when it gets fractured here, and it's also when it degrades, so at this point, so it will regain its properties. So it will repair itself and it will regain its properties, and it will act like an original material even after it fractured for the second time. So it will degrade its properties, and again it will attain its original properties as this process will go on. So this is the property of an ideal polymeric material. So with this, since due to some unavoidable reasons, I may not be able to continue the session. So now I am handing over the session to my colleague, Dr. Periasamy, who is working as an associate professor in our university. So he also has many years of experience in this field. So I would like to thank Dr. Adi for providing us this opportunity. So now I hand over the session to my colleague, Dr. Periasamy. Thank you.
Good evening to all. I am Dr. Periasamy. So who is working with Dr. Suresh, and we are working, recently we started the research in the smart materials. So our aim to achieve something new in the advanced research work. So we can go further for the presentation. Let's start about the smart materials. So smart materials are generally defined as self-organized materials stimulating itself based on the environment. It can be named as intelligent materials or advanced materials. Smart materials are categorized in basis of the properties such as active and passive materials. So fiber optic materials and antimicrobial fabrics, such kind of materials are belongs to the passive smart materials. They are just work as a stable material and conducting the electromagnetic waves, and they never respond based on their environmental stimulations, but they are most of the materials are highly stable materials. So this kind of materials belongs to the passive smart materials. And active smart materials is the another classification of the smart materials, which belongs to self-stimulation materials if fracture happens or broken happens. So these are Some examples, the piezoelectric materials and the shape memory alloys, such kind of pH. Sorry, the slides are very small. These are the materials belongs to the active smart materials. The ideal property of active smart materials can say self-actuation. To respond is an internal to the material rather than being external. Actually, once the fracture happens, it's respond immediately. So it's never expected for external force to it's actuated. So immediately it will respond, and smart materials respond to more than one stimulations or environmental effort at a time. It's called transiency. The selectivity property of smart materials is able to their response are different and observable. Other properties we can say, particularly shape changing, based on the environment, presence of internal stimulations, the material, if it's get damaged, it can change, recover the shape, the original shape of the material, and it can diagnose the itself, and healing started as soon as possible, immediately. That's why it's called immediacy property. So generally, we are started working. Actually, our research work focusing synthesis of self-healing polymers. Now, what is the self-healing polymers and the classifications we can see. So self-healing polymers. Sorry, the slides are very small because I've occupied a lot of places, so I can't able to see that. Self-healing polymers are mainly classified based on their healing process mechanism. So one is extrinsic healing method, another one is intrinsic healing method. So extrinsic healing methods, polymers based on their microcapsular healing process or microvascular healing process, and intrinsic healing process healing method is based on the internal stimulations are in the presence of heat or pH, like the conditions. The extrinsic self-healing materials contain healing agent or catalyst in capsules or vascular form into the matrix, wherein the agents releases on fracture of the material heal the structure. We can see here. Okay, I will explain later. This one we can intrinsic self-healing. The intrinsic self-healing materials requires no healing agent and shows ability to heal itself by cross-linking or reversible chemical bonding with external stimuli like water, light, heat, and some chemicals, etc. So the intrinsic self-healing material shows self-healing ability with the help of certain stimuli by formation of dynamic covalent bonding or supramolecular as well as physical interactions. So let's see the mechanism of intrinsic self-healing polymers. So we can see the extrinsic self-healing polymers mechanism presented here. The concept is we already everyone experienced with the Fevikwik. Fevikwik, we know that one. So it's a cyanoacrylate esters dissolved in a specific solvent like acetone, nitromethane, or DMSO, and isolated in a specific container. So once it get contact with the air, it get polymerized. So the same kind of concept is applying for extrinsic self-healing polymers. The polymer matrix is embedded with the polymerization catalyst and microcapsule in the polymer matrix. Polymerization catalyst and microcapsules inside the polymer matrix. Those microcapsules having the healing agents. During the healing process, the microcapsules break due to the stress in the cracking point, then react with a readily available polymerization catalyst. Because polymer catalyst is already available in the polymer matrix. So once the microcapsules break, it will interact with the so it's a sensor. So it will interact with the catalyst and it's get polymerized. So automatically, as a result, the crack get yielded, and we can get the polymer material as a like original material. The important point to note here, the yielded product must show the mechanical and conducting property of the original product, like a original product. So that is the limitations for this extrinsic polymer, extrinsic self-healing polymers mechanisms. So people's using initially dicyclopentadiene monomer as a content of microcapsule. So it can get, once it's break the microcapsule, it get polymerized. So these are the microcapsules already reported in the literature. So these kind of microcapsules can be prepared under specific temperature, under specific rotations in the agitations. There is a literature report, we can easily achieve this kind of microcapsules. There are some microcapsules, if it's broke like this, it's break, and then it get broke, and then the healing material get released, and it undergoes reaction with the catalyst. Generally, dicyclopentadiene and epoxy resins are used as a healing agent, and Griff's catalyst are used as a catalyst in the, it's embedded in the polymer matrix. So another development in the extrinsic healing process is microvascular network self-healing. Here, the healing agent encapsulated in the capillaries as a hollow fiber or hollow tube. The difference is the microvascular can store the difference is the microvascular than the microcapsule. It can store more healing agent, and we can control extensively externally. So if it's necessary, the healing agent can be pumped from the outside. Because if it's a small system, we cannot imagine like that. If we go for the applications like a big systems, it's a giant material. So the healing agent, the microfibers will be the hollow fibers will be a big size, and we can supply the healing agent from outside. So repetition healing can also be possible, even though healing agent finished in these conditions. So the healing efficiency will be calculated using this formula. It's reported in the percentage manner. So these are the healing agents, the micro containers we can still now used. See here the polyethylene amine and the dye are used for advanced microcapsules. The microcapsules containing various different containers inside the microvascular tubes or microcapsules. So it can heal efficiently than the traditional, like the initially identified microcapsules or vascular capsules. So these are the materials still now reported in the literature, and the epoxy resins also we can use. These are the epoxy resins. These resins are commercially available. So we can go to the intrinsic healing method. The concept of this intrinsic healing mechanism is considered more comparative in terms of manufacturing and applications, because the intrinsic healing process conferred to the polymer matrix. Here the function group of polymer matrix undergoes reversible reactions in the presence of external stimulations. The stimulations itself happens as a self-stimulations. The self-healing is achieved due to the resulting conformation changes of the dynamic dissociation and reassociation of stress-bearing bonds. The most used reversible reactions in the healing polymers are transition reactions, so Diels-Alder reactions, disulfide exchange reactions, and Michael Edison, silaxine, some metal and non-metal reactions. So another important thing for the criteria to achieve to design or achieve the healing, intrinsic healing polymers, or glass transition temperature must be a low, and chain mobility and chemical structures we have to consider to design the intrinsic healing polymer. Damage and repair process of intrinsic, this mechanism, this is the mechanism. So consider this is the original polymer material, and when this is the reversible polymer matrix. So when the reversible polymer matrix is damaged, two kind of local process can occur, namely chain cleavage and chain slippage. So during the chain cleavage, the polymer matrix gets a structural damage and form several function groups on the surface. These function groups can contribute to the subsequent interactions taking place during the intrinsic process, intrinsic healing process. On the other hand, chain slippage will happen due to the large number of chain matrix. If the crack happens, there is a chance to get chain slippage. So the chains, the active sites come each other during the slippage time, or some other factors can influence. Then once the reactive species connected each other, then the healing process will start. We can, as a result, we can get the self-healed polymer sheet or polymer material. It is almost like a the starting material, like unbreaked initial material. It contains same the mechanical property and conductivity properties. So this is the diagram explaining the thermodynamics of intrinsic self-healing polymers. The Gibbs free energy is less than 0, it means the above minus Gibbs free energy, we are getting the minus values less than 0. The spontaneous self-healing polymers will occur. If the Gibbs free energy is more than 0, the self-healing polymers will not occur. We have to apply, like a traditional materials, we have to apply the external force to recover the material, the healing process. And the solid line, the solid red line, depicts that the changes in delta G with the increasing repeating units of the polymer. If the repeating units increases, the self-healing polymerization is more easy. So if it's a higher repeating units in this, see the curve shows the higher repeating units is more self-healing properties. And another important point, in the low molecular weight and the low glass transition temperature, polymers are showing the better self-healing properties. So we can go for the synthesis of intrinsic self-healing polymers. In the year 2002, Chen et al. Research groups introduced a polymer with cross-linked structure capable of repairing through heat applications via Diels-Alder and retro Diels-Alder reactions. So initially they introduced, they used furan and melamine to produce the cycloadduct as a reactive groups in the polymer matrix. So the same research group experienced that low healing efficiency of this product, and it requires more energy, more heat energy to healing for carry out the healing process. So the same research group approached anthracene analogs with melamine products, the dione product, and it giving the high healing efficiency with efficient, good mechanical properties after getting healing the product. So these are the 4+2 cycloadduct products. We can discuss something about this 4+2 cycloadduct in the Diels-Alder reaction. So they introduced, the same research group introduced the cycloadduct with the stress based, and the reverse Diels-Alder reaction carried out under thermal conditions. So then later they identified the photochemical induced 2+2 cycloadduct for to prepare the self-healing polymers. So unlike the can say thermally induced reactions. Photo-induced reactions occur upon exposure to the specific wavelength of the light. This here they used one wavelength, and then for the cycloadduct they used one wavelength, and the Diels-Alder, reverse Diels-Alder, retro Diels-Alder, they used another wavelength. This photo responsive behavior offer alternative and tunable approach to achieve the self-healing in the polymer materials, and it offer the broader possibilities for designing advanced self-healing synthesis. And compared to the thermally induced self-healing, thermally induced Diels-Alder reactions, the photo-induced healing systems was significantly faster with a high recovery efficiency in the short time. Because in the traditional reactions also we can experience, compared to the wet reactions, photo-induced reactions are will be completed in the short time. So like that we can get the more efficient product in the short duration. So this is the Michael Edison reactions involving the thiol group. This is the unique reaction to achieve the chemically cross-linked polyurethane, because it can be used, it can be self-healed under or recycled under high temperature. So this product, this thiol product, are highly useful in the rubber industries, so making the vehicle tires. So the tires are always in the running conditions. It will be have to manage tolerate the high temperature. So if the crack happens, so the self-heal starts immediately, and then the tire's lifetime will be extended up to long-lasting lifetime you can get. And the 4+4 cycloadhesions are achieved under the photo-induced conditions. These are the initial reactions. Actually, yeah, these 4 cycloadhesion, Diels-Alder and retro Diels-Alder reactions are highly useful for synthesis or encourage the scientists to make self-healing products initially. Later, we can go see the trans-acidification reactions. So initially, the Leibler et al. Is a scientist who invented the Vitrimers. So Vitrimers is a strong and a flexible polymer. It can use as a it has enough mechanical strength and conductivity, and it can easily possible to recover itself. So the background of Vitrimer synthesis is the thermoplastics. Just the scientist feels that the thermoplastics are made of covalent bond molecules, the molecular chains, which are held together by weak interactions. So that's called thermoplastics. So that's why it can be easily flexible, and it can easily corroded by the environment. On the other hand, the thermoset polymers are made of molecular chains interacted by covalent bonds to form stable network. Thus, they have outstanding mechanical properties and thermal and chemical resistance. So Leibler observed these properties, and imagine if a polymer chain could have both the properties together, the resultant polymer could be the advantage of the both thermoplastics and thermosets. So initially they plan to synthesize some silica-like, they plan to develop silica-like network using well-established trans-acidification reaction. Is used by the reacting of epoxy and fatty carboxylic acids like dicarboxylic and tricarboxylic acids. The synthesis network have both hydroxyl and ester groups, which undergoes exchange reactions like trans-acidification reaction at high temperature. So as a result, the obtained materials are soft and stress tolerant, and it is highly stable and chemically resistant, and having high mechanical strength of the polymer. So on the other hand, we can change the reactions are suppressed to lower temperature, which can make materials soft. So see the images. This is the topology of the polymer. So the polymer can change their topology under thermal conditions. Initially, the bond between this, the sigma bonds, this is the sigma bond between the matrix. So it has 7-member ring, and again, under thermal conditions, it became a 6-member ring. The topology of the polymer has changed under thermal conditions, and it won't get break. So this is this behavior shows gives the thermally stable and flexible and high mechanical strength material. So actually, this research group published the video of these transformations. In the Google slides, I can't able to play the video. So that's why I make it a slides, snapshots to explain this bonding. And the advantage of another, the victimization have another advantage. It is recycling non-biodegradable polymers are, we can recycle like so we can change we can convert the non-biodegradable polymers as a vetrimeric polymers, because it makes advantage for the synthesis, because recycling of the non-biodegradable polymers are highly expensive, and it's hazardous to the earth. So to make that polymers for recycling, long-lasting material, this kind of materials can be converted by this vitamization method as a self-healing polymers. So here they introduced, polyester. They explain these reactions. The polyesters undergoes epoxy, the reaction with the epoxy resin in the presence of DBU catalyst at a high temperature. So we can get the vitamization. It's a cross-linked polymers having the it happens through the trans-acidification method. So in the synthesis of self-healing polymers, we can see the free radical reactions. So disulfide exchange reactions give the sulfide exchange of the polymers between two different kind of bonding matrix. If its cracks happens, this sulfide, they connected through the free radical polymerization, and we can get healing the product, healed product. And initially, this reaction was carried out with diamine disulfide compounds and some pentaerythritol derivative. These are the examples for free radical reactions, free radical reaction product. These are the silica exchanging product and some other materials. So imine exchange and oxime rebonding, like boron materials, can give the self-healing products through the free radical reaction. Now we can move to the part non-covalent bonding supramolecular chemistry. So the supramolecular chemistry, everyone knows that the bonding between the materials are non-covalent. So this product also giving the self-healing products. So these products generally identified the hydrogen bonding, the non-covalent hydrogen bonding, and host-guest interactions. Through the host-guest interactions, we can achieve this product, and through ionic interactions and pi-pi interactions of like the graphene materials. So it makes self-healing products. These products are highly applicable in the medical biochemistry and medicinal chemistry research field. Catalyst-free room temperature self-healing polymers are recently invented. So these previously what we discussed are the self-healing products may happen in the external stimulations. But here in 2014, the Spanish research group discovered or identified a catalyst-free self-healing product, so which is belongs to the sulfur exchange reactions. self-healing polymers that can spontaneously achieve quantitative healing in the absence of catalyst have ever been reported. So this is the first report. So the aromatic disulfide metathesis they used to achieve this, to synthesis or achieve this product. So this is the video graph, like a video explained to how the epoxy resin, the product, are very strong because they presented as a video. So here I am making slides. This is the product. They cut as a two part, and they kept at room temperature. After 2 hours in the room temperature, it healed together, and whatever the force we apply through the hands, it's difficult to separate. So that much healing properties. The scientists wondered about the quick healing capability of the synthesized polyurea elastomers like T-1000 robot in the Terminator movie. So because of their quick healing ability of their synthesized polymers, they named Terminator polymer of delivered to tribute to the T-1000 Terminator robot. So we can go for the applications of self-healing materials. So there are self-healing materials highly useful in the medicinal field. Presently, the artificial bone replacement can last up to the 10 to 15 years if the self-healing polymers, self-healing materials is smart materials like advanced materials we are discussing, because it says general categorized advanced materials applications. So the self-healing materials will give the long-lasting artificial bones and other organs. So in the dentistry field also, smart materials or that advanced materials will be highly beneficial for teeth and teeth filling and making teeth, because it's are highly always interacted with the teeth, always interacted with the humidity, the saliva in our mouth. So the self-healing material will be highly useful in this field, in the dentistry field. So in the drug discovery applications, we can see the combination of self-healing polymers and the nanoparticles are having excellent binding ability with the tissues, the human tissues, the live tissues, not only human, so animals also. So the fast responsible for wound healing applications also, it will be highly useful. So artificial organs also we can prepare through the 3D printing method. So in the aerospace, the smart materials are highly useful to make the lightweight vehicles, and we can make a lightweight satellites. It can it's easy to carry to the space, and it is a cost-effective material. It is a cost-effective, and the smart materials also reduce the space debris because it contains long-last lifetime. So automatically it's not destroyed quickly. And the same memory alloy smart batteries are highly useful to prepare the high-speed and low-speed vehicles, low-speed aerospace vehicles, because right now, presently, it's available the vehicles made like a flight or missiles or something made for high speed, not missiles, flight, and some other materials like aerospace materials can specifically made for high speed and low speed. So high speed materials we cannot play in the slower speed, and low speed materials we cannot run high speed. So because of the surface response of the response with the air molecules. So if you prepare the aerospace material, aerospace vehicles using smart materials, this problem will be solved. And it is highly useful for the military, because self-healing materials are used to prepare the very strong bulletproof vest, and smart skin can be useful for sensing agent and wound healing. So it can identify the wound healing and sensor to identify the explosives. And the supramolecular self-healing polymers are highly efficient for the biomedical applications. And micro robotics also we can prepare to make the efficient product. And the painting, the vitrimers, particularly vitrimers, are used in the painting field. Recently, these paintings are hydrophobic. So if a car, for example, this car paint or get damaged, it's coated by the vitimer, and within a week, in the height, if without doing anything, it can recover. These scratches are disappeared, and we can get a new product like that. So it also useful for the wall painting. So because of its hydrophobic material, due to the temperature, room temperature, it can recover. And self-healing polymers, smart materials are highly useful for the concrete engineering also, because instead of using traditional materials, they use the fly ash, silica fumes, and some other materials like what here mentioning the expensive minerals they're using, like magnesium oxide and calcium sulfonamides. It makes the heal the cracks once it's the healing happens, because the healing happens due to the presence of moisture like water and evaporation of carbon dioxide from the material during the time period, so it can get healed itself. And some biological materials also, biological pathogens also can be used for preparing the self-healing smart materials, particularly the bacillus bacteria, which is not harmful for our human body, and it's highly useful for preparing the water tanks and the tunnels and the highways, and particularly for this highways, which is always exposed by water. And also it can be prepared for airport runway, so to avoid the big loss in the accidents. So we are going to finish our lecture. It's already 1 hour 10 minutes finished. So this is the marketing nature of the self-healing properties. Apart from the research, and it must be a good business field. The literature says within the next decade how much billions we can earn. It will be a turnover in this self-healing materials field. So those who are interested, we can start the business in this field, not only research. So this is the reference. So initially, scientists who introduced the self-healing concept in 1981. So, and in 2002, after that, slowly growing, and 2002, Chen et al. Identified self-healing polymers through the Diels-Alder cycloadhesion, Diels-Alder and reverse cycloadhesion reactions. And this is White and research group introduced another self-healing compound, but I can't be able to visualize this because it's very small slides. And later, Leibler introduced that vitrimers. This is highly useful, and presently it's applicable for commercial purposes. And we would like to acknowledge our Kings of the University to provide the infrastructure to start the research in the self-healing polymer field. Myself and Dr. Suresh, we started with our research group. This is the initial stage, so still we are our travel to explore more about this research field, and we would like to thank for providing the infrastructure of this for us. And I would like to thank Dr. Adi for arranging this presentation, the conference, and offering this chance to present our ideology about the self-healing products and smart materials or advanced materials. And I would like to thank all of you for your patience to listen almost 1.5 hours with my presentation. Thank you, one and all.
Thank you, sir. Thank you to the speaker, Dr. Perisami, sir. It was very nice to know that Suresh got very good collaborator like you. Suresh told me that we work very closely and we are very good collaborators. And I request my friend to present the thing. Then I thought that, okay, someone will be there, but you presented very well, and we all happy to hear from you, sir. Thank you.